So today's discussion, we will be discussing about change in the atomic characteristics by the interaction with background fields. Till now, what we have learnt about is when atom starts interacting with background field, there is a non-zero of probability of transition from one state to another. However, we must note that the state which we are considering are no longer the eigenstates of the true Hamiltonian, because the true Hamiltonian involves interaction term with the field, the free field of the atom, a free Hamiltonian of the atom, and free Hamiltonian of the field itself. So net Hamiltonian is made up of various pieces. The eigenstates or excited state and ground state were just the eigenstates of one of the piece of the total Hamiltonian, which was the atomic part Hamiltonian. Now, net Hamiltonian, as we will see below, will be just Hamiltonian of atom plus Hamiltonian of field and plus an interaction term. So therefore, only eigenstates of the first term do not constitute the eigenstate of the full Hamiltonian. And as we have seen, if the field is time dependent, it's even in vacuum state, its effect is to give rise to an effective Hamiltonian to the atomic system, which is as good as a fluctuating quantum correlation coming into the picture. So therefore, it will be a time dependent Hamiltonian term, which would be present for the atomic part's effective dynamics. So that constitutes the total Hamiltonian or effective Hamiltonian rather of atomic system, becoming a time dependent Hamiltonian, and therefore there is no eigenstate of the system because this is a time development. The dynamics is there explicitly in the Hamiltonian, and therefore steady state picture does not hold. So therefore the energy gap between the atom state, which is delta E between excited state and the ground state, was the energy gap before the atom started interacting with the field. Once the interaction starts, the delta E is no longer the energy gap between the eigenstates of the Hamiltonian of the atom. Therefore, we should be aware of the fact that the energy gap itself changes due to the interaction of the field, even if the field is in a vacuum through vacuum fluctuation. This goes by the name of lamp shift, that the energy state of the eigenstate difference, energy eigenvalue difference between the atomic states keeps changing due to interactions of vacuum fluctuations. And over long time average, it will settle to a well-known expectation value that we will see in this set of discussions. And for just obtaining a more apparent version of how to compute this shift in the atomic spectra, we will be adopting something called as the DDC formalism, which are named after three people, Dalibor, Contreras, and Cohen-Tanouji's approach of how to deal the effects of background fields on the states of atom itself. Okay, so let us get going with this understanding that now we are no longer just looking for transitions alone, but are concerned with the change in the characteristic properties of the atom itself. Okay, so now, as we know, the total Hamiltonian has many terms. It has a atomic free part, which is free part of the free Hamiltonian of the atom, HA, which in its spectral decomposition is written as h bar omega by 0/2 plus plus, this is the excited state, and minus h naught omega by 2 minus minus, which is the ground state. So I'm just defining the structure like the ground state is given with the symbol ket of minus, excited state is given with the symbol of ket of plus, and the energy separation between them is something whose frequency separation is omega naught. So I'm just setting the zero of the energy at the mid of this separation, such that the excited state is plus h naught omega by 2 eigenvalue, and ground state is minus h naught omega by 2 eigenvalue. I can pull out h naught omega as a common factor, and you will see I will be left with 1/2 of plus plus minus 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 gets outer product. So therefore, this is a compact operator representation of the atomic part of the total Hamiltonian. This R3, you can remember, you can realize that it is very much the spectral decomposition of the sigma 3, the third polymer. Okay. Now, under time evolution, if you want to look at this Hamiltonian will undergo a time evolution such that R3 over here will change in time. So how would I compute the total time evolution of this HA? I will take its commutator with respect to total Hamiltonian, and whenever this R3's commutator with total Hamiltonian will arrive, I will call this R3 of tau. So this is the total time evolution of the free part of the atom. Similarly, we can try to look at the free part of the quantum field. The quantum field's free Hamiltonian in its normal ordered version can be written as just integration over all modes. Each mode is bringing energy h bar omega k, and how many such modes are excited, ak dagger ak. This is the number expectation. Okay, this is the standard exercise which we had done in the scalar field when we discussed, and this is the normal order Hamiltonian, which ignores the delta zero part coming into the Hamiltonian. Okay, here let us notice once more that this omega k which is appearing over here is the frequency of the mode as seen from the lab frame. From the atom frame, it is omega k prime, whose expression which we obtained in the previous discussion session. But right now I have given a decomposition in terms of the lab frame. Either I can Lorentz transform everything d3k primed, omega k primed, ak dagger and ak, and obtain the Hamiltonian for the field as seen by the atom, or we can try to find out what it looks like in the eyes of the atom itself. So the atom at the description of the field is given by the Hamiltonian HF, and in frame of atom its time evolution is controlled by parameter tau, which is just the previous Hamiltonian times an extra factor dt upon d tau. So the free field's Hamiltonian as seen by the atom is the free field Hamiltonian as seen by the lab observer times this dt upon d tau. How do I obtain that? Just approach this problem from the structure that the Lagrangian since action has to remain preserved in any frame, so Lagrangian has to transform with this relation under Lorentz transformation, and therefore Hamiltonian derived from it will also inherit that relation, dt upon d tau factor. Okay. Now, in this way, the field was initially written in the lab frame modes. So, lab frame frequency, lab frame mode scale of the wave numbers, and the operators ak and ak dagger. Okay, that was the scalar, and that's why since it is scalar field, there is no extra dx mu factor. The Jacobian or the lambda matrix transformation which will associate it is why try to jump from one frame to another. So these two things are just free field, the free field's Hamiltonian and the free atom's Hamiltonian as seen in the frame of atom itself. Now we come to the interaction term. Previously we had written the interaction term in terms of the lab observer. Now we want to cast it back in terms of the atom. So the same thing will happen. One will write down the, let us say, monopole operator. This time I am just writing it as some parameter of control mu, and R2 operator whose definition I am just coming in a minute, and times phi. This is the phi, the field as seen by the atom at different location in its own coordinate system. So this monopole operator we have seen before. I am just writing it with some parameter mu times some operator. So this operator R2 typically is a transition matrix operator. That means it's only off diagonal elements survive. Its a spectral decomposition is not a spectral decomposition. Its decomposition is such that in the eigenbasis of the free Hamiltonian is R plus is a raising operator in some sense, that it takes ground state and projects it to excited state, while R minus is the inverse of that, which takes the excited state and projects it back into the ground state. So therefore this monopole operator or the transition operator can be written like R minus minus R plus with iota by 2 factor just to restore the hermiticity. This is just sigma plus and sigma minus, if you recall, in terms of polymatrices. This is the interaction term with respect to the field. So now we have everything in terms of atom. Now atom has this description of physics going along, that it has one Hamiltonian HA, it has a one field around it whose description is given by the phi at location x of tau, and there is an interaction term which now is being written in terms of atom's clock as well. So we have everything at hand from the point of view of atom. Remember, we have taken this philosophy that we will compute things of our interest in atoms rest frame where all the Schrodinger mechanics for atoms happens. So therefore, the perturbation theory which we develop for non-relativistic systems keeps applying in the frame of atom. It will not be applicable if I start doing physics from the lab frame because atom is relativistically moving. So a better strategy is to jump into the atom rest frame and compute things out. Okay, so now we write down all the relevant commutators which will appear in if I try to write down the time evolution of these operators, because remember, time evolution of these operators is controlled by these operators commutation value with the total Hamiltonian. So various commutators will appear in that. So let us list down all the commutators. Since R2, R3, R1, R plus and R minus are very similar to what we have seen for the Pauli matrices, their commutations are also following that. That means R3 and R plus and minus commutator will be up to plus minus sign R plus minus. That means if I'm taking commutator of R3 with R plus, I will get R plus. R3 with R minus, I will get a minus of R minus. R plus and R minus will be twice of R3 and so on. So this set of commutation relation is handy because now, as we discussed, total Hamiltonian is the collection of all the Hamiltonian of individual atom, the field and interaction all written in the atom spec. So we go ahead and quickly write down the time evolution of all the operators of interest. For example, if I want to write down d d tau of R plus or R minus, then I would take the R plus or R minus commutator with its total Hamiltonian. Remember, this R plus is made of Pauli matrices which concerns only with the atomic sector. So it will just commute with the free field sector. This only contains field operators, this only contains atomic operators, this contains a mixed term, both atomic operator and field operator. So when I do a commutator with R plus, if I take the commutator of R plus with the total Hamiltonian, that R plus operator will have a non-trivial commutation with the first term and the third term because these involve operators from atomic sector. With second term, it would be trivially commuting because field operators are different from the atomic operators. So therefore, when I try to compute the R plus, it will undergo R plus commutator with HA and R plus commutator with HI. So R plus commutator with HA will give me this term, which is the free field evolution, free evolution of the atomic system. But due to interaction, now this new term will be generated, which is R2's commutator, R plus commutator with the interaction Hamiltonian. Okay. Similarly, when I try to write down the time evolution of R3, which appears in the Hamiltonian of the atom. So time evolution of this, if I want to obtain, I should write down the d tau of R3. Every time evolution is right now being done in the clock of atom because this is where the Schrodinger evolution holds. So again, the same thing which we will do take this R3, obtain its commutator with the total Hamiltonian. R3's commutator with HA will be 0 because HA itself is also R3 up to a constant. HA is also R3. So R3 will commute trivially with HA. R3 will also commute with HF because HF is made from different operators, field operators only. They do not concern the atom. So only thing which will be surviving non-zero with non-zero value is R3's commutator with HI. And remember what was HI? HI was just R2. Some mu times R2. So you will see that the total term on the right hand side will be the interaction Hamiltonian commutator of that with respect to R3, and that's why this term will survive. Lastly, if I look for the field operator itself, its evolution, again the A operator will undergo the commutation relation with respect to all the three terms. First term does not concern with the field, so it will vanish. The commutator will be 0. HF and A commutator gives the free field evolution. So this is the free field time evolution of the ladder operator, which we had seen previously. But now, due to this interaction term alive, this AK will have a non-zero commutation relation with respect to HI. Because in HI, there is not only M, but also phi term present, which also have A and A dagger and whatnot. So if you write in terms of that, I will have a non-trivial commutation relation between the a and the phi, which will be appearing into the third term. And this will be the total derivative of the time derivative of the ak operator. So these are the relevant operators time evolution which appear in each of the pieces of the individual Hamiltonian. A Hamiltonian is made from R3, F Hamiltonian is made from AK and AK dagger, and HI Hamiltonian is made from R plus R minus. So therefore, and phi. Therefore, we have the temporal derivative of all the relevant operators which appear at different places in the time evolution. So therefore, now we are ready to write down the total time evolutions of anything. Just to be curiously informed, you can see that every piece over here, when we write down, breaks into two parts. This is free part. This would have been as the usual evolution if there were no interaction, plus controlled evolution due to the interaction. This is 0 plus. 0 was the free evolution. If there were no coupling of atom and field, this was the 0 term. So therefore, this evolution is coming from the coupling term. Lastly, the field operator also has a free part and there is a coupling part. So all the operators which we have written down can be written that they have a free evolution and there is a sourced evolution. Sourced evolution in the sense of due to coupling. Free evolution and sourced evolution. Free evolution and the sourced evolution. And you can see that this is a differential equation structure. So if I start writing all the R operator as free part plus source part, all the A operators as free part and source part, then it will become an equation which will be connecting various free part and source part. So you can see if I write down here, let us say, or here, it will have a RF of 2 plus R sourced of 2. Similarly, RF of 2, RF of plus minus and RS of plus minus. Similarly, for phi, you will write phi F of S and phi F plus phi sourced. So you will see this kind of things will appear and it will become an iterative equation. That means here R plus free part or R plus sourced part will depend on the source part and free part itself as well. So you see there is a coupling between the first part and the source part, free part and the source part, and so on. So if I try to write down if I want to write down the, let us say, free part and the source part up to linear order in interaction. So therefore, I will put in this when I'm writing over here. I put it RF plus RS, everywhere RF plus RS, phi F plus phi S and twice copies of RF plus RS. Then I will see there is a free parts evolution which is controlled by free part only. Free parts evolution which is controlled by free parts evolution which is controlled by free part. But source part contribution, if I'm looking for source term evolution, that means from here if I want to write down dRs upon d tau, then there are various terms which are coming. dRs upon d tau will be made from first term omega naught and Rs here. Then there is a phi f which can multiply either RF here, RS here, RS here, RF here, or RS here, RS here. So there are three operators which are appearing one after another. If I open the commutator, and all of the three operators can be broken into free part and source part, free part and source part. And source part, if you see, it is coming through the interaction term. That means the parameter of control mu appears once. So if I want to truncate things at the leading order, only one operator of source nature should appear and two operators of free nature should appear. So ultimately there are terms which is, for example, phi of free, and then commutator I would have a R2 of free and R plus of S, let us say. There could be term like phi F and both of them are R2s are R2 and R plus are sourced. R plus is sourced, and similarly there could be a term phi s which will be either multiplying this term or multiplying that term. But you see, when I try to write down for phi s again, phi s itself will satisfy a differential equation structure controlled by the AKs as well. So if I have to keep feeding the value of phi s or rs or the r plus minus s here and r2 of s, it will become higher and higher power in mu, because rs becomes non-zero only when there is a mu. So that means whenever rs appears, it will come with a mu, and outside there is already a mu. Okay, so here, therefore, when I have to write down the thing at the leading order, only one operator is allowed to become sourced operator, and even that operator will be multiplying an extra mu to it. So that means at the leading order thing, mu with all free part would be order mu. Anything, if any of this thing develops a rs or phi s or r3 of s, then basically what we are meaning that it is next order term, it is order mu square term, and so on. So therefore we have to be very aware of the fact that all the rs which are appearing are iterative equation of rf plus rs, and at the leading order rs should be obtained from 1 power of mu. That means all the operators appearing inside are just free part, and all free parts multiplying together with the coupling parameter mu generate for you what is the source part. Okay, this is leading order result. In principle, you have to feed this relation and on again. There was truly phi was setting, r was setting, and r was setting. If you want to write down in terms of their free and source part, you will obtain many terms which are all higher order. So this is the philosophy we do, and at the leading order, all the operators appearing are made into free operators, and the source operators are just derivative quantities from the free operator. So using that, we can write down the leading order source correction to the quantum field itself as iota mu times all the operators which are appearing over here. Remember, from here we can just multiply mode function and dagger of that to obtain the field. So it will become multiplied with uk over here, do the dagger thing, the field will come and sit over here, and all the quantities from the source part will be converted into their free forms. So you will get this operator determining what is the sourced correction to the field. The free field theory was giving me the field operator as the usual this thing. This is the free part. To that, a new correction has been added because of its interaction with atom, which cares about atomic operators. Atomic operators tell the field how to modify at the leading order. So this is the correction brought to the field itself. Okay. Similarly, corrections will be brought to any operators of atom as well. Again, at the leading order, we will do all the correction term with their free forms appearing in the commutator. So for instance, if I am talking about some operator G of an atom, this is atomic operator, it is not the field operator. Then again, I have to find out what is its time evolution rate. I will take its commutator with the total Hamiltonian. Total Hamiltonian is made from 3 pieces. First piece involves atomic operator, so G might or might not commute with that. Third operator also involves atomic operator, so G might or might not commute with that. But middle term, which was the free field Hamiltonian, that only involves field operators. So atomic operator, so G will definitely commute with that, so I don't write that term. Okay, so now this is the trivial evolution under no interaction. This much was just the standard evolution. Now if I focus what is the change brought by coupling, so I can write down dg upon d tau of coupling, that is just this, that term, and I open up what is the interaction term. Interaction term, remember, was mu times the operator R2 times phi. It doesn't matter whether I write phi on the left or right of R2, because R2 and phi are different Hilbert space operators. R2 acts on the states of atom, phi acts on the state of the field. So therefore I can write it either way. Okay, so as you see, again we have the same philosophy which we discussed about, that this is made from phi f and phi s. So there is a phi s sitting over here as well. Okay, now remember the expression of phi s which we just derived. Phi s depends on the atomic operators as well. So by the time when I said that phi and atoms are different operator, that was different Hilbert space operator. That was a statement for free field theory. In free field theory, phi is completely made of operators which do not care about what state atom is. But now when the interaction is on, this phi, which is written over here, is made up from a piece which also contains an atomic operator. So this time it is no longer true that if I write on the left or the right, it doesn't matter, because this time cost of phi going across R2 and field commutation is non-zero. In absence of interaction, if interaction were not there, then phi s part would have been vanishing, and then this would have been zero. The commutator would have been zero. Then writing left or right is immaterial. But since we are writing the field also get corrected due to the interaction of atom, the phi s part being written on the left of this commutator or on the right of this commutator are two different things. They are not the same thing. That story was true only for the free field part. So therefore, we do not know which way to write. Either I write here or I write there, or some 30% here, 70% there. So some operator ordering ambiguity arises out of it. Which way to write this product? So we do ad hoc splitting. Lambda fraction of that is written on the left, and 1 minus lambda fraction is written on the right. Lambda could be chosen any number depending upon what observations nature tells us. So a priori there is no way to write, no, as of now, that which way I should split. Okay. So now again do the same game again, that if I open phi as phi f plus phi s, open this thing as R2 free plus R2s, and all the operators over here, then you will find out that the dg of tau, the coupling term, that also splits in two portions. One determined by field part, free field part in some sense. This is vacuum fluctuation part is called. And then there is a interaction of atom and the field. This is called radiation reaction term. So ultimately the coupling term also splits into two nice terms, which are like this. Okay. So what the vacuum fluctuation term is made from the free field part. So what did I do? I just split it up. I just split the field operator into its two segments, free part and the source part. So therefore all the terms will, in this expression, phi appears only once. So it's linear in phi. So therefore it will split up into its free part and its source part. So therefore I will have two equations, one for free part and one for source part. The source part equation is called the radiation reaction term, and the free part term is called the vacuum fluctuation term. Now you see, if I want this dg upon dt, which is an operator's time evolution, to be Hermitian as well, at this stage we can fix, there is no way but to fix lambda to 1/2, because you see, if lambda is any other value, take the dagger of this thing, it will not come back to itself. So this is the observation the DTC approach realized, that in order to have a Hermitian description of the time evolution of operator, lambda is necessarily required to be 1/2. Okay. So therefore, this gives you a good description. Put this to 1/2, put this to 1/2 as well. This gives you a good description of how a field operator or atomic operator rather would change its character due to interaction with the field itself. For instance, if I want to write down what is the change in the atom's Hamiltonian itself completely. So again, it will be obtained from these two terms. There will be dH of dt of atom vacuum fluctuation part, which will be totally determined by the free field part. And all the operators appearing over here will be put to their free field value. Okay. And a radiation reaction part, which will be made from the sourced Hamiltonian. Here the G would be written as the Hamiltonian itself, and Hamiltonian, remember, was what? It was something times R3, omega naught times R3. So wherever this you see, you will put a R3. So therefore you will see R3 commutator will appear, and their splitting 1/2 will appear. And here, if I look at the radiation reaction part of the total Hamiltonian, a phi s is here, which is controlling, phi s is appearing here and phi s is appearing here. And recall the phi s itself was obtainable from the commutator between phi f at two different locations multiplying the RT. So you have to put this expression of phi s back into the total change in the Hamiltonian. So radiation reaction term will be made from the commutator between the fields, their free parts commutator at two different times, and then the splitting of R2 appearing across commutator of R2 and R3 in the symmetric way. Okay, so that would be the radiation reaction change in the Hamiltonian. This will be due to vacuum fluctuation. Compactly, it can be written as, you can see the structure which is appearing. The vacuum fluctuation is made from the anti-commutator of the free fields and commutators of this and that. Okay. While for the radiation reaction, the opposite happens. Commutator of the field appears and anti-commutator of this object R2 and commutator of R2, R3 appears. So you see R2 and commutator of R2, R3. Its commutator appears here and field anti-commutator appears here. And the exactly opposite appears in the radiation reaction. So we can just define quantities like field anti-commutator with CF and field commutator with respect to field commutator as chi f. And if suppose I want to know the atomic Hamiltonian rate of change if the field is in the vacuum state, because atomic Hamiltonian rate of change cares about which state atom is and which state field is. So I am prescribing the field is in vacuum state. So previously the anti-commutator and the commutator were appearing. Now those anti-commutator and commutator will get squeezed between the vacuum states. So that I am calling CF and chi f. So commutator's expectation in vacuum and anti-commutator's expectation in vacuum, they go and sit over here. So I'm taking expectation here and expectation in the preceding term here. To obtain, at least the field segment has been fixed to be the vacuum. This is due to vacuum fluctuations, and vacuum commutator and vacuum anti-commutator is telling me what is the total rate of the change of Hamiltonian operator of atomic system. So this is happening due to vacuum fluctuations and radiation reaction from vacuum. Both things put together generate this much change in the Hamiltonian of the atom. Now what we will do, we will take this change in the Hamiltonian and find out due to this change how much change in the eigenspace separation occurs, and that is the amount of Lamb shift an atom will suffer, which we will evaluate in the next class. Okay, so I stop over here.